Hello and welcome to this video where we'll come into overfitting and underfitting. What does this mean? These two terms are very important in machine learning, deep learning, and in AI in general. That when you're training a model, there's a risk that you train it too much or too little, or your model is too complex or too simple. The idea is to find a balance between these, that you get a model that can generalize well. I'm talking a lot of new terminology now, if this is the first time you hear about this, but it's okay. We will go more into depth of what these different terms mean and give some example and more intuitive understanding, and not going in too much on the mathematical parts in this video. Let's move on to the theory. Here I am in the slide. The art of finding a model not too complex to overfit and not too simple to underfit. It's a balance. You need to find a model. And when I say find a model, it could mean that there are some parameters to tune, that you choose different parameters. It could be that you choose another model that is better for the fit. Just go into an example that is quite simple at first. If you have the data that looks like this, how to fit it? What you can see is that, a polynomial of degree 2 might fit very well. However, if you, for example, have a polynomial of degree 1, then you have a line that looks like this. It could fit, for example, like this, and that it misses a lot of data. It doesn't fit very well. This is called underfitting. Or you could make a line that looks like this, but you miss the data and in this part. This is a nonlinear relation, and using a line, it's too simple to capture the data's variance. The data's variance cannot be captured by just a line. The line is way too simple. Basically, we underfit. This is called underfitting. And in underfitting, we have the model, it has low attention to the training data. It doesn't have the attention on all the training data. We get the underfitting. What this is that we have high bias and we have low variance. I won't go into the mathematical details and exact explanation of what this means, but just note that this is what we have in the underfitting. We have higher bias, then we have a more simpler model, and we have low variance. This means we have a simpler model. We make it into polynomial regression. What does this mean? We can get a curve that looks like a second order. We transform the feature space into second degree, and this is called polynomial regression. Now we don't have a line. Instead, we have a second order curve. For example, here is one feature, and the one feature, we transform it into x1 and x1 squared. We'll go into practicality, how to do that later on, but just make sure that this is possible to do, that you use some feature engineering and you can make your one feature become two features by using some kind of transformation, okay? Here we have ax1 plus bx1 squared in order to capture this curve. This is a second degree polynomial, or second order polynomial. And what we have here is that we lower the bias and we increase the variance because we make the model more advanced. We make it more complex. It captures the variance better. That we have a higher variance and we have lower bias. However, should we pick second order, or should we pick third order or fourth order, etc.? How much should we go? What if we make a very complex model? What will happen? For example, like this. We capture all the points, but is this good? We have very high degree. There is a very low error in the training data. Yes, of course, we have fitted it very well. There's a low error. But however, we have fitted to the noise. That is not good, because what happens when we want to predict something? We say we want to predict a point that maybe should be here, but because it have fitted to the noise, it finds another point. It's not very good. We have overfitting. And it means that it cannot generalize well. That you can see it as, you can take an analogy. You're studying to tests. And what you do is that you only study on the old exams. You're very expert on the old exams. You even know the patterns that the teacher will create a new exam. However, when you come to the exam and there come another question that you have studied on, you don't know how to generalize your knowledge because you only know how to answer those questions in the previous exams. You haven't studied the curriculum. Unfortunately, you have overfitted to the training data and you cannot generalize and use your knowledge. Here we have higher variance and we have low bias. We have very high variance and very low bias here when we have very complex model. There's a clear overfitting here. It generalizes badly. What you need to do is you need to find a balance, a bias-variance trade-off. This is a term that you will work with a lot if you're going into data science and want to find models that will generalize well. And then you will go into, you will have this in mind all the time. Bias-variance trade-off. The bias is basically a difference between the average prediction and the correct value. And the variance is how much the model changes if training on multiple data sets. This is what it means, and you need to find a balance between this. And as you saw before, basically when you have higher bias, you have simpler model, and when you have lower bias and higher variance, you have more complex model. You need to find a model that is not too complex and not too simple. That is the main idea to pick from here. If we have high bias and low variance, we oversimplify the model. It's underfitting. While if we have low bias and very high variance, it fits to noise and we get overfitting. This is the main idea to bring with you. Okay? What can you do? For example, for this example with polynomial, you could do elbow plot. This is a good way to visually see. You have an error. It's the bias plus variance plus irreducible error. And what you can do, you cannot do something about the irreducible error. You can do something with bias and variance. This is our focus. And what you can do is that you choose a metric, for example, RMSE that we work with in a lecture with a coding lecture. Root mean squared error if it's in regression. You find the root mean squared error and you do it for different degrees for the training data. And what you can see is that, for example, for 1 degree, we have very high RMSE. For 2, we have lower. And for 4, we have lower. And then for 4, it increases again. This is an elbow here. This is a minimum. And you train on the... actually, I said wrong before. It's not the training data that you do this on. You do this on the validation data to find the degree. Here you have elbow plot. Okay, this is the elbow. This is the degree that is the sweet spot. Here you have the bias-variance trade-off. You pick degree and you will have the model that is corresponding mostly to this validation data. And then when you have picked this, the elbow is the degree is the hyperparameter, and then you can use this to train on all your training and validation data that you can predict on the test data. This means that we have train val test split. It's splitting in three times. Yes. Here we pick degree 3 for our polynomial regression. In this lecture, we have gone through overfitting and underfitting and the art of finding the sweet spot, the model that balances between the bias and variance. We have bias-variance trade-off. If you're going into more data science, this is more what you want to do to find the good model for your data. And then you give this to, for example, the data engineers, the ML engineers, etc., that they can use this model in production. And in this lecture, we have also gone into an example using polynomial regression. We went into increasing the degrees to see how you can go into getting more complex model, but not too complex model. And then we've gone through elbow plot to see where to find the sweet spot. I hope you got some intuition about how the overfitting works and underfitting. This is very important also when you go into deep learning, when you train on a massive amount of data. And then it seems that why doesn't the model becomes better? It even becomes worse. Yes, there's some methods to decrease to firstly detect overfitting or underfitting and then decrease it and finding the sweet spot. This is the foundational theory about this. Thank you for watching this video and see you in the next one. Bye.